Okay, so let's suppose that we have a function, and let's suppose this function looks like this. Okay? Now, here's what we have. We have an independent variable x and a dependent variable y. Y depends on x. So we say y is a function of x. And we know how to differentiate this. Now I'm just going to use this prime notation here, but what we're going to say is, okay, y prime is equal to 2. And we're done with that one, right? So there we have y defined explicitly in terms of x. It's just y equals. Now, I want to play this little game here. I want to say, well, what if I raise both sides to the 4th power? Okay? So if I do that, now I've got 4y on this side. No, not 4y, y to the 4th. Sorry about that. I've got y to the 4th. And over here, I've got 2x plus 3 to the 4th. Okay. Now, I want to just look at both sides of this and look at finding the derivative. Now, if I look at this side over here on the right, the derivative is going to be, we're going to use the chain rule. So this is going to be 4, 2x plus 3 to the 3rd. But we're not finished because now I got to multiply by the derivative of the inside. Okay? So what I've done is I've taken the derivative of that right-hand side. Now I'm going to now take the derivative of this left-hand side over here. Now notice what I would need to do. Y is equal to something. In fact, we know what it's equal to in this case. It's equal to 2x plus 3. But let's suppose I didn't know that. Let's suppose I was just proceeding like, okay, I know that y depends on x. I don't know how, but I do know that I'm going to go 4y cubed times the derivative of y with respect to x. And let's just call that y prime. Okay? So notice I differentiated both sides, but the left-hand side is the same as the right-hand side. It's just I've got a little bit different notation. It looks a little different. But notice that I've got 4y cubed. Here's 4y cubed, right? Because we said that y is 2x plus 3. Times y prime. Well, this is y prime right there, right? So notice that even though the left-hand side and the right-hand side, they look different, they're really saying the same thing. It's just on the left-hand side, I'm not given y explicitly. I know y is equal to something in terms of x. I don't know what, but I'm just going to call it y prime. Now, this kind of gives you insight into what we call differentiation of functions that are implicitly defined. In other words, y is not explicit, y equals something in terms of x. You have y, but it doesn't have an explicit equals. In other words, it's not just y equals something. So let me give you an example here. Let's suppose that we have x plus y equals 4. Now here, I don't just have y equals something. And let me make this a little bit different. Let me just make this x squared plus y equals 4. Now this is a very simple one. And we could solve this for y. Now notice, if I solve this for y, I get y equals 4 minus x squared. And then I could do this. I could say y prime is equal to negative 2x. So that's super easy for us. Here, y was not explicitly defined in terms of x. So we did what's called, we differentiated, we still solve for y and we differentiate it. But now, I could approach this a different way. I could leave everything as it is and then differentiate implicitly. I'll call it implicit differentiation. And notice, what I'm going to do is I'm going to differentiate everything I can get my hands on. I come to the x squared, and it's just 2x. Now, because x is just, it's the independent variable, I'm finished there. I don't need to do anything else with it. In other words, x is not some function of something else. we differentiate it like usual. But I come over here and I come to y. Now with the y, I'm just going to say, okay, the derivative of y. Okay? Now I come over here to the 4, derivative of 4 is 0. Okay, does everybody see that? Now I can solve for y prime, and if I do, notice I get negative 2x, which is the same. Okay? So on the one way, we were given y explicitly in terms of x, and on the other hand, we weren't. But we arrive at the same answer. Now, let's look at a problem that's a little more complicated. We'll just add to the complexity just a tad. Let's suppose that we have a circle, a unit circle. X squared plus y squared equals 1. So there's a unit circle. And what I want to do, we'll make the problem a little more interesting. I want to find the slope of the tangent at, let's say, theta equals pi over 4. No, let's not make it pi over 4. Let's make it pi over 6. Okay? Now remember, that corresponds, on the unit circle, that corresponds to the particular ordered pair. That corresponds to the square root of 3 over 2, comma 1/2. Okay? So x is the square root of 3 over 2, and y is 1/2. We remember that that angle on the unit circle corresponds to that. Now, what I want to do, I know that's the top part of the circle, so what I'm going to start off doing is the old way of differentiating something like this, where we would need to solve for y. So I'm going to solve this for y. And when I do that, I get y squared equals 1 minus x squared. And because it's on the top part of the circle, I know y is positive up there, so I can just say, well, y equals the positive square root of 1 minus x squared. Right? Because it's on the top part. I don't have to do plus or minus. Pi over 6, that's the top part of the circle. Now, I'll differentiate. Okay? So I want to find the slope of the tangent. So here I go. Y prime is equal to 1/2 1 minus x squared to the negative 1/2 times negative 2x. Okay? So realize what we did. We differentiated the outside. We got 1 minus x squared to the 1/2. We differentiated that and then multiplied by the derivative of the inside. And notice that these little fellas cancel. So we have a nice slope here. Our slope formula is now, look at this, negative x over the square root of 1 minus x squared. There's our slope formula. And at this point, I could just put in x, which is the square root of 3 over 2. And I'll go ahead and do that just so that we can see the algebra here. So our slope is going to be negative square root of 3 over 2. And down here, 1 minus square root of 3 over 2 squared. We'll see if we can figure out what the slope is. Now we're doing this the old way, just with the chain rule and having y explicitly in terms of x. Now, I'm going to do this now. I've got negative square root of 3 over 2, and down here I've got 1 minus 3 over 4. Now, I'll tell you what I want to do from this bottom. I'm going to factor out a 1/4, right? Because I know the square root of 4 is 2. So dig what I'm going to do now. Down here, I've got 1/4 times 4 minus 3. Okay, does everybody see what I did? Notice I can factor out a 1/4 as long as I remember to compensate for it, right? Like if I distribute this 1/4 back through, I do get a 1 back here, and then I get a 3/4 there. So it didn't hurt anybody. Now if I take out the 1/4, I get 1/2 square root of 1, right? So that's nice. And then notice I don't like the fact that I've got this complex fraction, so let me just multiply the top and the bottom by 2. Whoops. And it looks like what I get is negative square root of 3. for my slope. That's my slope. Now that makes sense because if you're talking about the slope of a tangent at pi over 6, you would have a negative slope, right? If you picture a tangent. Okay, so anyway, it all started with us getting the formula for the slope of a tangent. Okay? Now, let's go back. And to be honest, it was kind of a pain to have to solve this thing for y. You know, we didn't like having to do that. So let's differentiate using what we know about implicit differentiation. That's what I'll call it, implicit differentiation. So here we go. I'm going to differentiate the first term. And because it's the independent variable, I don't need to do anything more with it. But here I'm coming up to the y. Now I've got to worry about the chain rule. 2y times the derivative of the inside equals 0 over here. See? You go through, you differentiate everything, but when you come to the y, you have to remember the chain rule. Okay, y is a dependent variable. It's dependent upon x, so I have to do the chain rule. Not with x, but with y. Now I want to solve for y. And dig this. Now I get 2y, y prime, is equal to negative 2x. And of course, I can divide out the 2. And look what I get. I get y prime is equal to negative x over y. Okay? So here's what my derivative looks like when I approach this thing from the implicit standpoint. Okay? I've got this implicitly defined relationship, and there's what I get. And you might say, hey, that doesn't look like the derivative that we got a minute ago. The derivative we got a minute ago looked like this. Okay? Well, remember, though, that y, here's y. Let me put it in nice green. This is y, right? So, yeah, we did get the same thing. We did get exactly the same thing. It only looks a little bit different. So now, if I then find the slope, here's the slope. It's going to be negative square root of 3 over 2, that's the x, over 1/2. Yeah, and that's negative square root of 3. So just like before. Now, you might be asking yourself, well, why do we even need implicit differentiation? Because we know how to differentiate just fine if y is explicitly defined. Well, the problem is sometimes the solving for y can give us a challenge. So let's think about this one. Let's think about x squared y cubed plus, let's say sine y. So here's one, and what we want to do is we want to find dy dx. Now this one, if you try to solve for y, it might give you a moment of pause, right? Can you say, how can I solve that for y? Well, fortunately, we don't have to, because here's what we want to do. We just put on our implicit boots, and we come through here, and we differentiate everything we can get our hands on. There's an x. Yes, the derivative of x is 1. Now, we come over here. I've got a clump. This is a product. So we're going to have to use the product rule. So let me do this. This is going to be 2x y cubed plus 3y squared y primed x squared. Now just take a minute and just digest there what I did. I took the derivative of the first, x squared, the derivative of that's 2x times the second. And then I want to take the derivative of the y term, which is 3y squared y prime, okay, times x squared. Okay, now I mosey on over here. The derivative of sine is cosine. Don't forget the y prime. Every time you differentiate something with a y in it, you're going to have to put a y prime there. Well, the reason you do it is because y is the dependent variable. It equals something, so we have to do the chain rule. Okay, now you might say, well, congratulations, you have a nice mess. Well, here's the thing. Every time we do this, we're going to have a linear power of y prime. So that means we can solve it fairly easily because we can solve linear equations. So here's what I'm going to do. I'm going to take everything that's not a y prime and move it over. If it's not got a y prime in it, I move it over. So I've got 1 minus 2xy cubed. Everything that's got the y prime in it, I have it together with the other y primes. So here we go. We've got 3y squared x squared y prime plus cosine y prime. Now the good thing is I can factor out the y prime. Okay. So here I go. Let me see what I got now. I've got 1 minus 2xy cubed. I'm going to factor out the y prime. Okay. And remember, all we're trying to do is say y prime or dy dx. We're just understanding this y prime is in term with respect to x. All I'm trying to do is say the derivative equals something. Well, here I am. I'm ready to go now because I can do this. I can say 1 minus 2xy cubed over this thing. Look at that beauty. There we have it. There's your derivative. Okay? Implicit differentiation. That's what that is. Okay? Any questions? Okay, now one more thing we want to look at, and that is the second derivative. Now, the second derivative can be a handful. We haven't done a lot of these, but just remind you, if we have a function, let's suppose we have a function x to the fifth, let's say, and we want to talk about derivatives. Here's what we can do. We can say, okay, dy, and let me just say this is f of x equals y. So we could say this. We could say f prime of x is equal to dy dx, which is 5x to the fourth. Okay? So just a couple of notations. Now, for the second derivative, remember we can do a double prime. And this is the way it's going to look with Leibniz notation. It's going to be d with a little 2 up here and a y there. And down here, a dx with a little 2 up there. And the reasoning behind that is we're saying, okay, I want the derivative of a derivative. And it's kind of intuitive that it would look like d squared y, right? It's kind of intuitive it would look like this. And on the bottom, just dx squared like that. So that's why we have this notation. But this would be 20x cubed. And then we could say, well, I want the third derivative. So that would be d with a little 3. Look like that. And that would be 60x squared. Now, you might say, well, okay, this prime thing, I can see how that would get out of hand. Like, what if I want the 7th derivative? Am I going to have 7 primes? What about the 100th derivative? 100 primes? This is ridiculous. Well, at some point, like the 4th derivative, you start saying things like this. You put a little 4 in there. Yeah, like that. And then, you know, the Leibniz still looks the same. So this is 120x, like that. So we haven't talked a lot about higher order derivatives, so I thought I'd just take a minute and just go over that with you. So what we want to do is we want to say, okay, what if you have an implicitly or explicit situation here? X and Y, they're entangled some way. We don't see y equals right away. We just have a situation like this. Now, we've already dealt with this problem before, but let's suppose what we want to find here is we want to find the second derivative. And we have y given to us in this form. So here's the way we approach it. The first derivative, same as always. Now, we have already found the first derivative. So I'm going to kind of skip that. And what we found was, remember, that y prime is equal to negative x over y. This is what we found earlier. There's no reason to reinvent the wheel. Now, if you want the second derivative, you do exactly what you would think. you just differentiate. I mean, so what I'm going to do, I'm going to differentiate the left-hand side here, and it's double prime. But now when I come over here to this other side, I've got myself a quotient rule to deal with. So here I go. Let's get ready. So the derivative of the top is -1 times the bottom. Okay? Minus the derivative of the bottom times the top. All over the bottom squared. Now you have to watch your signs, of course. That's a negative x. I could have factored the negative out. It just depends on what, how you want to approach it. That probably would have been a better way to do it, wouldn't it? Okay. But I didn't, so we'll just go with it. Okay. Okay, now what we've got here is the second derivative, but we don't want this to be in terms of a y prime. What we want is we want our second derivative to be in terms of x and y. So here's what we do. At this point, I'm going to now say, okay, this is -y. Let me make this a plus. Y prime in place of y prime, I'm going to put -x over y. And then I've got this x here. Now notice, I use this negative and got a plus, but then I still have my derivative, which is negative, all over y squared. Okay. Now, one more thing we want to do here is we want to do a bit of simplifying. We hate complex fractions like this. They're unseemly, right? So what I'm going to do then is I'm going to just multiply by y. Here, here, and here. Just multiply by y for all three, everything. It's like I'm multiplying the top and the bottom by y. And then I distribute the y. So dig what happens now. Let's see here where we are. Up top, I've got -y squared. Now this cancels. Minus x squared over y cubed. Okay, everybody see that? Okay, now, really, we're done. That's good enough. However, for this particular problem, it's irresistible to go one more step because we know that x squared plus y squared equals 1. That's the original problem. So let me just factor a negative out of here. And replace that x squared plus y squared with 1. And that's a little bit easier. That's nice. That's very satisfying to go that next step. Okay. Okay, any questions? So there's the second derivative. Now, later on, we're going to talk more about the definition or what the second derivative tends to tell us. But right now, we're just kind of getting used to the differentiation, the algebra of it and all. Any questions?